Imagine you are traveling at the speed of light, not as a metaphor, not as a thought experiment borrowed from a physics textbook. Truly imagine it. Photons streaming across the vacuum of space, 186,000 miles every second, the fastest anything in this universe can move. At that velocity, you could circle the Earth 7.5 times in a single second. You could reach the Moon in about 1.25 seconds, Mars at its closest approach to Earth in roughly 3 minutes, the Sun in 8 minutes and 20 seconds. Now keep going. Neptune falls behind you in about 4 hours of travel. The heliopause, the outer boundary where the Sun's solar wind finally exhausts itself against the incoming pressure of interstellar space, passes in roughly 17 hours. You are now outside the solar system entirely, beyond the farthest edge of the Kuiper belt, traveling through the vast dark corridor between stars. Behind you, the Sun has dimmed to something indistinguishable from the surrounding field of stars. A single point of yellow, white light in a field of points, unremarkable. Hold that velocity. 4 years pass. You arrive at Proxima Centauri, the nearest star to our Sun. 4 years of traveling at the speed of light just to reach the next nearest point of light. You have crossed 4 light years. On a scale model in which the Sun is the size of a grapefruit, the nearest star would be approximately 500 kilometers away, roughly the distance across the continental United States, 4.5 times over. Keep going. 100 years of light, speed travel, 1,000, 5,000. You are now deep within the Milky Way galaxy, moving through one of its spiral arms, surrounded by stars separated by distances so vast that even at your present velocity, crossing from one star to the next takes years. The stellar density here is roughly 1 star per several cubic light years, and those light years between individual stars swallow every intuitive sense of what proximity means. 26,000 light years from Earth, you cross the central bulge of the galaxy, a densely packed aggregation of ancient stars orbiting Sagittarius A star, a supermassive black hole with a mass 4 million times greater than the Sun. The core glows in infrared and radio wavelengths, a turbulent region of compressed stellar material, high-energy radiation, and magnetic fields of extraordinary intensity. Stars here orbit the central black hole on elliptical paths, taking only a few years to complete, moving at velocities of several thousand kilometers per second, velocities at which, if you were standing on the surface of one of those stars, you would see the entire galaxy wheel overhead in a human lifetime. And then you emerge on the other side, still moving at the speed of light, still crossing the disk of the Milky Way, still inside the same galaxy you started in. The disk extends approximately 100,000 light years from edge to edge. Some recent estimates now push this figure to as much as 180 or 200,000 light years when the outer stellar halo is fully accounted for. After 100,000 years of continuous travel at the speed of light, you have barely crossed the galaxy you were born inside. That galaxy, the Milky Way, contains between 200 and 400 billion stars. Its dark matter halo, the invisible gravitational scaffolding that holds the entire stellar system together, extends perhaps 300,000 light years in radius. It has been forming stars for roughly 13 billion years. It will likely continue forming stars for several billion more, until its gas reservoir is exhausted or disrupted by its future collision with the Andromeda Galaxy, which is currently approaching on a roughly 4 billion year timescale. The Milky Way is, by every experiential standard available to a human being, unimaginably vast. It is also, in the full context of what the observable universe contains, unremarkably small, ordinary, a mid-sized spiral galaxy, one among hundreds of billions of others, sitting in a modest galaxy group on the outskirts of a minor supercluster. In an unremarkable region of the cosmic web, there is a galaxy approximately 1 billion light years away from us. A galaxy that would take a beam of light not 100,000 years to cross, but somewhere between 5 and 6 million years. A galaxy so enormous in its physical extent that the Milky Way, placed inside it at some random interior position, would be a minor perturbation near its outer edge, a small spiral system lost in the vast diffuse halo of a far larger structure. A galaxy whose stellar mass alone may exceed 100 trillion solar masses, equivalent to somewhere between 200 and 500 Milky Ways combined, a galaxy whose dark matter envelope encompasses a volume of space that makes the concept of galaxy feel taxonomically insufficient, as though the word was coined for smaller things and is now being stretched beyond its intended meaning. It sits at the center of one of the most massive known galaxy clusters in the observable universe. For billions of years, the gravity of that cluster has channeled infalling galaxies, hundreds of them, perhaps thousands over its full history, toward this central point, where they have been consumed, torn apart, and absorbed. The galaxy at that center has grown not merely large, but structurally dominant, its gravitational influence extending across millions of light years, its outer halo built from the dispersed remains of galaxies that no longer exist as independent entities. It is called IC 1101. To understand what that designation means, to truly absorb its significance rather than simply register its dimensions, requires first understanding the physical processes that create objects of this scale, and why the largest galaxies in the observable universe are found exactly where IC 1101 is found, at the gravitational centers of the most massive concentrations of matter that the universe's 13 billion-year history of structure formation has so far produced. The universe, roughly 13.8 billion years after the Big Bang, is not uniformly distributed. In its earliest moments, fractions of a second after the initial singularity, it was extraordinarily smooth. The temperature and density of the primordial plasma varied by only about 1 part in 100,000 from point to point, a degree of uniformity so precise that if the early universe were the surface of a sphere the size of the Earth, the height variations of its terrain would be less than a meter. Yet those tiny fluctuations were enough. Gravity, operating across billions of years with absolute fidelity to its inverse, square law, amplified them relentlessly. Regions of slightly higher than average density attracted more matter, which increased their gravitational pull, which attracted still more matter. Regions of slightly lower than average density lost material to their denser neighbors. What began as near perfect uniformity evolved, over the full span of cosmic history, into one of the most intricate large-scale structures ever described or imagined, a cosmic web of filaments, sheets, and voids that spans the entire observable universe. The universe, roughly 13.8 billion years after the Big Bang, is not uniformly distributed. In its earliest moments, fractions of a second after the initial singularity, it was extraordinarily smooth. The temperature and density of the primordial plasma varied by only about 1 part in 100,000 from point to point, a degree of uniformity so precise that if the early universe were the surface of a sphere the size of the Earth, the height variations of its terrain would be less than a meter. Yet those tiny fluctuations were enough. Gravity, operating across billions of years with absolute fidelity to its inverse square law, amplified them relentlessly. Regions of slightly higher than average density attracted more matter, which increased their gravitational pull, which attracted still more matter. Regions of slightly lower than average density lost material to their denser neighbors. What began as near perfect uniformity evolved, over the full span of cosmic history, into one of the most intricate large-scale structures ever described or imagined, a cosmic web of filaments, sheets, and voids that spans the entire observable universe. The seeds of this structure are detectable directly, imprinted in the cosmic microwave background, the thermal afterglow of the early universe that fills all of space with a nearly uniform glow at a temperature of 2.73 Kelvin, the relic radiation of a time roughly 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and photons to travel freely through space for the first time. The temperature variations in the CMB, mapped with extraordinary precision by the COBE, WMAP, and Planck satellites over 3 decades of increasingly sensitive observation, are the direct imprint of those primordial density fluctuations, the seeds from which every galaxy, cluster, and large-scale structure in the universe ultimately grew. The hot and cold spots of the CMB map correspond to the initial density perturbations, slightly overdense regions that would eventually contract under gravity to form the structures of the present universe, slightly underdense regions that would expand to become the voids. Abell 2029 and IC 1101 grew from one of those overdense seeds, a slight enhancement in the density of the primordial plasma that was present from the first fraction of a second of the universe's existence, and that gravity has been amplifying and concentrating ever since. The transition from those early seeds to the present galaxy cluster involved not only the simple collapse of baryonic matter under gravity, but the earlier and faster collapse of dark matter, which began clustering before the ordinary matter was even free to do so. The tight coupling between photons and baryons in the early universe prevented baryonic density fluctuations from growing until after the CMB was released, while dark matter, which does not interact with photons, began building its potential wells earlier. The dark matter halos that formed first served as the gravitational scaffolding into which baryonic gas subsequently fell, cooled, and formed the first stars. This sequence, dark matter halos first, then gas infall, then star formation, is the standard picture of galaxy formation, confirmed by observations of the high, redshift universe and by numerical simulations of structure formation that reproduced the observed large, scale structure of the universe with remarkable fidelity, when the parameters describing dark matter and dark energy are appropriately tuned. The filaments of this web are threads of dark matter and gas stretching hundreds of millions of light years, along which galaxies form and drift like condensations along wet string. The sheets are two-dimensional structures at the intersections of multiple filaments, thin membranes of enhanced galaxy density separating enormous empty voids that contain almost nothing in the way of luminous matter. The voids themselves are vast, regions hundreds of millions of light years across, where the expansion of the universe has overwhelmed local gravity, where galaxy formation was suppressed by the absence of sufficient density fluctuations, where space is nearly empty in the sense that it contains very few large-scale structures, and at the nodes, the points where multiple filaments converge from several directions simultaneously, the greatest concentrations of mass in the universe accumulate. These are the galaxy clusters. A galaxy cluster is not simply a group of galaxies that happen to be found in the same region of space at the same cosmic moment. It is the most gravitationally bound large-scale structure known to exist, hundreds to thousands of galaxies held together by the combined gravity of their dark matter halos, their stellar mass, and the enormous quantities of extremely hot gas that permeate the space between their member galaxies. This intracluster gas, called the intracluster medium, or ICM, exists at temperatures ranging from tens of millions to hundreds of millions of degrees Kelvin, heated by the gravitational compression that accompanied the cluster's formation and maintained by ongoing shocks and turbulence as material continues to fall in from the surrounding cosmic web. At these temperatures, the gas glows in X-ray wavelengths, emitting enormous fluxes of high-energy photons that can be detected by space-based X-ray observatories across distances of billions of light years. The intracluster medium is one of the most diffuse substances ever measured. A cubic meter of it might contain only a few hundred to a few thousand atoms, compared to roughly 27 million trillion atoms in a cubic meter of air at sea level. Yet the total mass of this gas, distributed across a cluster spanning several million light years, can exceed the combined stellar mass of all the galaxies within the cluster. Galaxy clusters are, in terms of their mass budget, predominantly dark matter, the invisible, gravitationally active substance that interacts with ordinary matter only through gravity, whose existence is inferred from its gravitational effects on everything around it. After dark matter, clusters contain hot gas. After hot gas, they contain stars. The luminous galaxies that define a cluster to visual observation are, in terms of mass fraction, a relatively minor component of the total system. IC 1101 sits at the center of Abell 2029, a rich galaxy cluster catalogued by American astronomer George Abell in his landmark 1958 survey of clusters identified on photographic plates from the National Geographic Society Palomar Observatory Sky Survey. Abell's catalogue, containing two 7012 clusters, was the first systematic attempt to quantify and characterize the large-scale distribution of galaxy clusters across the sky. Abell 2029 lies approximately 1,070,000,000 light years away in the direction of the constellation Virgo. It is classified as a rich cluster with a high estimated galaxy count, and it is among the most X-ray luminous clusters in the observable universe. Its intracluster medium radiating X-ray energy at a rate suggesting enormous total gas mass and high temperature. The total mass of Abell 2029, dark matter included, is estimated at roughly 1 quadrillion solar masses, 10 to the 15th power, making it one of the most massive gravitationally bound structures currently identified. At its center, IC 1101 reigns. The presence of the largest, most massive galaxy at the center of the cluster is not coincidental. It is the predictable, theoretically understood outcome of a process called hierarchical structure formation, the process by which large structures in the universe grow not by collapsing from primordial clouds of gas in a single event, but by the repeated merging of smaller pre-existing structures into progressively larger and more massive ones over cosmic time. This process begins with the smallest dark matter halos, forms the first dwarf galaxies, merges those into larger systems, and continues through every mass scale up to the clusters and superclusters of the present universe. Dark matter halos are the fundamental units of structure in this picture. They form first, collapsing from the density fluctuations of the early universe under the influence of their own gravity. Ordinary matter, gas, falls into these halos, is compressed, cools, and forms stars. The first stars and galaxies appear within the first billion years after the Big Bang, living brief, brilliant lives in relatively small dark matter halos. These halos are then themselves attracted to one another by gravity, their trajectories bending inward, eventually leading to close encounters in which the halos interpenetrate and merge, their stars and gas mixing, their combined potential settling into a new, larger equilibrium. The merged system forms a larger galaxy within a more massive halo, which can then attract and absorb additional galaxies. The cycle repeats hierarchically at every scale. In a galaxy cluster, this hierarchical process reaches its maximum current expression. The cluster's central region is the deepest gravitational potential well in the local cosmic environment, the point toward which all infalling material is ultimately directed. Galaxies that form or are captured in the outer regions of the cluster move toward this center over billions of years, driven by the cluster's overall gravity, their trajectories eventually converging toward the central potential minimum. Many of them, upon arriving in the dense central environment, encounter the existing central galaxy, a massive system that has been sitting at this gravitational focal point for much of the cluster's history, accumulating material from every earlier episode of infall. IC 1101 is the product of this process operating for roughly 10 to 12 billion years at one of the densest, most gravitationally favorable locations currently observable. It sits at the bottom of the gravitational potential well of Abell 2029, the convergence point of countless trajectories traced by infalling galaxies over cosmic time. Every galaxy that has entered Abell 2029 along a radial or near radial orbit has contributed, to some degree, to what IC 1101 has become. When a smaller galaxy falls into the gravitational field of a massive central galaxy, the interaction depends critically on the mass ratio and orbital parameters of the encounter. In major mergers, encounters between galaxies of comparable mass, the gravitational distortion is catastrophic for both systems. Tidal forces elongate each galaxy into streams of stars, bridges of material, and shells. Gas clouds from both systems collide directly, compressing and triggering intense bursts of star formation that can briefly increase the combined galaxy's luminosity by orders of magnitude. The supermassive black holes at the centers of both galaxies are drawn toward each other over millions of years, eventually settling into a closely bound binary that then spirals inward as it radiates gravitational wave energy, ultimately merging in a brief but extraordinarily energetic event. The remnant settles, over several 100 million years, into the roughly ellipsoidal form that characterizes massive galaxies like IC 1101. Minor mergers, encounters in which a much smaller galaxy falls into a much larger one, are less dramatic but cumulatively enormously important. A smaller galaxy entering the outer halo of IC 1101 experiences intense tidal forces that strip stars from its outer reaches, gradually dispersing its stellar material through the outer envelope of the larger galaxy. the stripped stars are distributed into the diffuse halo of IC 1101, adding to its total mass and physical extent without significantly increasing its central surface brightness. Over billions of years, hundreds or thousands of such minor mergers contribute enormous quantities of stellar mass to the outer halo, building it into the extraordinarily extended structure it is today. A key physical process enabling this accretion is dynamical friction, the gravitational interaction between a body moving through a background of other bodies. When a galaxy moves through the dark matter and stellar background of IC 1101's halo, it gravitationally attracts the surrounding material, creating a slight overdensity behind its direction of motion, a gravitational wake. This wake exerts a retarding force on the moving galaxy, removing kinetic energy from it and causing its orbit to gradually decay. Over time, the infalling galaxy spirals inward, depositing its mass into the growing central galaxy at the end of a long spiral trajectory. The efficiency of dynamical friction depends on the mass of the infalling object relative to the background density. More massive infalling galaxies experience stronger friction and spiral in more rapidly, while smaller systems may orbit for longer before finally being absorbed. The combination of major mergers, minor mergers, and tidal stripping over roughly 10 to 12 billion years has built IC 1101 into the structure. It is today an ancient, massive, slowly fading elliptical galaxy with a compact, extremely luminous central region, the accumulated stellar mass of its most recent major mergers, surrounded by an extended, diffuse stellar halo composed primarily of material deposited through minor mergers and tidal interactions. This outer halo is the component responsible for much of IC 1101's claimed diameter of 5 to 6 million light years. The surface brightness of this outer halo falls steeply with increasing distance from the center. In the innermost regions of IC 1101, the stellar density is high and the surface brightness is substantial. The galaxy is clearly visible in even modest telescope observations, appearing as a concentrated elliptical glow near the center of the Abell 2029 cluster field. Moving outward, the stellar density decreases, the surface brightness falls, and the galaxy becomes progressively harder to distinguish from the background. By the time one reaches the outermost measured extent of IC 1101's stellar envelope, the surface brightness has dropped to levels that approach the technical limits of current imaging capabilities. Surface brightness, the brightness of an extended object per unit area of the sky, is one of the most critical parameters in extragalactic astronomy, and it is fundamental to understanding both what we know about IC 1101 and the inherent limitations of that knowledge. Unlike the total flux from an object, which decreases as the square of distance, surface brightness is approximately conserved with distance in Euclidean space, modified only by cosmological effects in the expanding universe. This means that a galaxy with intrinsically low surface brightness will appear faint not simply because it is distant, but because its stars are genuinely spread out at low density, an intrinsic property of the object. No increase in telescope aperture will improve surface brightness sensitivity in the same way it improves sensitivity to point sources. The night sky imposes a fundamental limit on the detection of extended low surface brightness sources, even from the darkest accessible astronomical sites. The Atacama Desert of northern Chile, the summit of Mauna Kea, the remote high plains of Antarctica. The sky is not perfectly black. Airglow from the upper atmosphere, the cumulative emission of unresolved distant galaxies forming a diffuse background, scattered starlight, and instrumental noise all contribute to a sky background brightness that prevents the detection of extended sources whose surface brightness falls below roughly 8 to 30 magnitudes per square arc second in optical wavelengths. Objects fainter than this threshold are effectively invisible, absorbed into the uncertainty of the background. This limit is directly relevant to the measurement of IC 1101's diameter. The figure of 5 to 6 million light years represents the extent of the galaxy's detectable stellar emission, the radius at which the surface brightness of its stellar halo rises above the detection threshold. The actual physical extent of the stellar distribution, defined as the distance from the center at which the stellar density drops to some small multiple of the intergalactic field density, may be larger. The dark matter halo certainly extends further still. Dark matter halos in the most massive galaxies and clusters are estimated to extend to radii 10 to 100 times the visible stellar extent. What we measure when we claim a diameter for IC 1101 is, in the most precise language available, the diameter of the portion of IC 1101 that we can currently detect with existing instrumentation. IC 1101 was first catalogued in 1891 by astronomer Lewis Swift, who observed it as a faint nebulous object during one of his systematic searches of the northern sky. It entered John Dryer's Index Catalogue, the extension of the New General Catalogue that organized thousands of additional nebulae and star clusters identified in the late 19th century, as an unremarkable entry. At the time, the nature of nebulae was still actively debated. The resolution of the great debate about whether spiral nebulae were objects within the Milky Way or independent island universes lay 3 decades in the future, awaiting Edwin Hubble's measurement of Cepheid variable stars in Andromeda in 1923. The entry for what would become known as IC 1101 in that catalogue carries no notation of extraordinary size or importance. The universe's largest known galaxy was, at its entry into the scientific literature, a footnote. IC 1101 is classified morphologically as a CD galaxy, a designation introduced by William Morgan in 1961 to identify a specific class of supergiant elliptical galaxies found at the centers of rich galaxy clusters. The C in the classification denotes a supergiant luminosity, while D indicates a diffuse, extended envelope. CD galaxies are distinguished from ordinary giant ellipticals primarily by the presence of this anomalously large outer envelope, an extended stellar halo that follows a different, shallower brightness profile than the inner regions, suggesting that it was not formed in the same way as the main body of the galaxy. This outer envelope is now understood to be the product of the accumulated tidal debris from the galaxy's long history of mergers and accretions, precisely the process described above. IC 1101 is the most extreme example of a CD galaxy currently identified in the observable universe. Its morphology in optical images is smooth and featureless compared to spiral galaxies. There are no prominent disk structures, no spiral arms, no obvious star-forming regions or gas lanes in the main stellar body. The stellar population of IC 1101 is dominated by old, evolved, metal-rich stars, stars that formed billions of years ago when the galaxy's progenitors were actively converting gas into stars at high rates, and that have since exhausted their hydrogen fuel and settled into the later stages of stellar evolution. These old stellar populations radiate primarily in the red and infrared portions of the spectrum, giving IC 1101 the characteristic red color of a passively evolving elliptical galaxy. The epoch of intensive star formation that built up IC 1101's stellar mass was concentrated at early cosmic times, primarily in the redshift range from about 2 to 5, corresponding to the period between roughly 1 billion and 3 billion years after the Big Bang, when the universe was young and gas was both abundant and relatively cool. In that era, the progenitor systems of what would eventually become IC 1101 were forming stars at rates potentially thousands of times higher than the Milky Way formed stars today. The energy output of these starbursting systems was enormous, their ultraviolet emission blazing across the early universe, their winds and radiation driving enormous quantities of gas out of their halos and enriching the surrounding intergalactic medium with heavy elements produced in stellar interiors and distributed in supernova explosions. That active period is long over. The cold gas that fueled it was consumed in star formation, blown out by stellar feedback, or heated to temperatures that prevent it from efficiently cooling and collapsing. IC 1101 today forms stars at a very low rate, consistent with the broader population of massive elliptical galaxies in clusters, which are generally quenched systems in which star formation has been suppressed by a combination of gas exhaustion, AGN feedback, and environmental effects. The galaxy is aging slowly, its stellar population fading on billion-year timescales, its color growing slightly redder as the more luminous blue and yellow stars die and only the dimmest, reddest stars remain burning on their extraordinarily long main sequence lifetimes. At the center of IC 1101, as at the center of essentially every galaxy above a certain mass threshold, there is a supermassive black hole. The mass of this central object is not directly measured with the precision available for nearby, well-resolved systems like Sagittarius A, star in the Milky Way, or the black hole at the center of M87, whose mass was famously measured through gas dynamics and which was imaged by the Event Horizon Telescope in 2019. For IC 1101, the mass is inferred primarily from scaling relations, empirical correlations between black hole mass and the properties of the surrounding stellar system, particularly the velocity dispersion of stars in the bulge. The tightest known such correlation, called the M-sigma relation, relates the black hole mass to the velocity dispersion of stars in the galactic bulge through a power law that holds remarkably well across more than 4 orders of magnitude in galaxy mass. Applied to IC 1101, whose stellar velocity dispersion is large even by the standards of massive ellipticals, the M-sigma relation predicts a central black hole mass that may range from several tens of billions of solar masses to potentially 100 billion solar masses in the most extreme scenarios. For comparison, the Milky Way's Sagittarius A star has a mass of approximately 4 million solar masses. The black hole at the center of M87, one of the largest nearby ellipticals, is approximately 6.5 billion solar masses, itself already a factor of more than 1,000 larger than the Milky Way's. The black hole at the center of IC 1101 likely exceeds even M87's by a factor of several. Such a black hole grew through a combination of gas accretion and black hole mergers. When 2 galaxies merge, their central black holes are eventually drawn toward each other by dynamical friction acting on the surrounding stars and gas. They form a binary system that, hardening through gravitational interactions with stars in what is called the final parsec problem, a theoretical challenge involving how the binary loses enough energy to reach the separation at which gravitational wave emission can drive the 2 black holes together efficiently. Whatever the detailed mechanism, merging galaxies eventually produce merged black holes. The final coalescence releases a burst of gravitational wave energy that, for the most massive black hole mergers, would be detectable in principle by future low-frequency gravitational wave detectors like the Laser Interferometer Space Antenna. The gravitational wave signature of IC 1101's formation history is encoded, in some sense, in the background gravitational wave field of the universe, a cosmic memory of 1 billion years of hierarchical merging. When a supermassive black hole is actively accreting material, gas falling in from the surrounding environment, feeding a luminous accretion disk, it becomes an active galactic nucleus, or AGN. At its most luminous, this process produces a quasar, an extraordinarily energetic object that can outshine the entire stellar population of its host galaxy by factors of hundreds or thousands, visible across the entire observable universe at the highest accretion rates. The progenitor systems of IC 1101, during their era of intense star formation and gas infall, almost certainly hosted quasar-level nuclear activity. The epoch of peak quasar luminosity in the universe, again concentrated at redshifts between about 2 and 4, corresponds directly to the epoch of peak star formation and most vigorous gas dynamics in early galaxies, suggesting that both processes are driven by the same underlying supply of cold gas. The feedback between AGN activity and galaxy evolution is one of the most actively studied subjects in modern astrophysics. A sufficiently powerful AGN can drive gas out of its host galaxy in large-scale winds that can quench star formation, heat the surrounding gas to temperatures that prevent further cooling and collapse, and inject energy into the intracluster medium across scales of hundreds of thousands of light years. The jets produced by radio-mode AGN, large-scale outflows of relativistic plasma that can extend for millions of light years beyond the galaxy's visible extent, are particularly effective at heating the intracluster medium through the cavities and shocks they drive into the surrounding hot gas. In Abell 2029, the intracluster medium has been studied in detail using observations from the Chandra X-ray Observatory, which achieved sufficient angular resolution to map the thermal and density structure of the hot gas with a precision that was impossible before the satellite's launch in 1999. The X-ray morphology of Abell 2029 shows a smooth, centrally concentrated distribution with a cool core, a region of several 100,000 light years radius centered on IC 1101, where the gas temperature drops from the cluster average of roughly 8 keV to about 2 to 3 keV, and where the gas density is sufficiently high that the cooling time drops below the age of the cluster. This cool core is what remains of what was once expected to be a cooling flow, a large, scale inflow of cooling gas toward the cluster center that was predicted by early cluster models but was found when X-ray spectroscopy became precise enough to test the prediction directly to be far weaker than expected. Something was heating the gas and preventing the most dramatic cooling. The most compelling candidate, supported by the observation of X-ray cavities and radio lobes associated with the central AGN of IC1101, is feedback from the central active nucleus itself, a self-regulating cycle in which cooling gas fuels AGN activity. The AGN heats the surrounding gas. The heating reduces cooling. The AGN becomes less active. The gas cools again, and the cycle repeats on timescales of tens to hundreds of millions of years. To return now from the physics of cluster gas dynamics to the pure scale of IC1101 itself, to hold the object in the mind without immediately reaching for the next larger structure requires deliberate effort. Light from a star in the outermost detected regions of IC1101 takes approximately 5 to 6 million years to travel to the galaxy's bright center. This is a single galaxy, a beam of light, traveling at the absolute maximum speed permitted by the laws of physics, requires 5 to 6 million years to cross this object from one side to the other. The Milky Way, by comparison, requires 100 to 200,000 years for the same journey, a factor of 20, 5 to 50 shorter. To cross IC1101 to end at the speed of light would take longer than the entire span of human existence from our earliest hominid ancestors. It would take longer than the extinction of the dinosaurs. It would take as long as, or longer than, the evolutionary history of multicellular animal life on Earth, placed where the Milky Way is, with IC1101 centered on the same position currently occupied by our galactic center. The outermost extent of IC1101 would reach 2.5 to 3 million light years in every direction. The Andromeda Galaxy, currently located approximately 2.5 million light years from the Milky Way, would sit within or at the very edge of IC1101's stellar halo. The Triangulum Galaxy, the Large Magellanic Cloud, the Small Magellanic Cloud, the dozens of known dwarf galaxies that orbit the Milky Way, all would be embedded within a single galaxy. The entire local group of gravitationally associated galaxies, which spans roughly 10 million light years in its full extent, would be largely encompassed within IC1101's boundaries. This comparison is geometrically accurate. The local group is the collection of approximately 80 known galaxies, including the Milky Way and Andromeda, which are gravitationally bound to one another and which occupy a region of space comparable in linear dimensions to IC1101. When we talk about IC1101's size, we are describing an object whose physical extent is comparable to that of an entire local galaxy group, not a region containing many independent galaxies, but a single coherent gravitational structure, dominated by one central potential. The stellar mass of IC1101 reflects this extraordinary scale. Current estimates, derived from its total optical and infrared luminosity combined with models of its stellar population, suggest a stellar mass somewhere between 50 and 100 trillion solar masses, with the uncertainty reflecting both observational limitations and theoretical uncertainties in mass to light ratios for old stellar populations. The Milky Way's stellar mass is estimated at roughly 50 billion solar masses. IC1101's stellar mass thus exceeds the Milky Way's by a factor of roughly 1,000 to 2,000. Its total mass, including dark matter, is estimated at 10 to 50 quadrillion solar masses, the equivalent of somewhere between 10,000 and 100,000 Milky Ways. But while these numbers are impressive, they may undersell the true scale of IC1101's influence in its environment. A galaxy is not merely its stars, it is the full extent of its gravitational sphere of influence, the region over which its potential shapes the motion of surrounding material. For IC1101, embedded in the massive potential of Abell 2029, that sphere of influence is difficult to disentangle from the cluster's broader gravity, but the contribution of IC1101 itself to the central potential of the cluster is substantial. It is the dynamically dominant object in its environment, shaping the orbits of neighboring cluster galaxies, determining the temperature structure of the intracluster medium at small radii, and setting the pace of the AGN feedback cycle that regulates cooling at the cluster core. The question of whether IC 11.1 is definitively the largest galaxy in the observable universe remains, in the most rigorous scientific sense, open. The claim is well supported and broadly accepted among observational astronomers specializing in large, scale structure and cluster galaxies, but it carries the qualifications that attach to all measurements at the limits of current instrumentation. Several other CD galaxies in rich clusters are competitive candidates depending on the specific definition of galaxy size applied. The brightest cluster galaxy of Abell 085, of Abell 0665, and of several other massive clusters have measured stellar halos, extending to radii of several hundred to more than 1,000 kiloparsecs, the boundary region where IC 11.1's unique claim begins to face competition. The question of whether IC 11.1 is definitively the largest galaxy in the observable universe remains, in the most rigorous scientific sense, open. The claim is well supported and broadly accepted among observational astronomers, specializing in large, scale structure and cluster galaxies, but it carries the qualifications that attach to all measurements at the limits of current instrumentation. Several other CD galaxies in rich clusters are competitive candidates depending on the specific definition of galaxy size applied. The brightest cluster galaxy of Abell 085, of Abell 0665, and of several other massive clusters have measured stellar halos extending to radii of several hundred to more than 1,000 kiloparsecs, the boundary region where IC 11.1's unique claim begins to face competition. It is worth pausing on what the measurement process actually involves, because the technical challenge of measuring IC 11.1's size is itself instructive about the limits of knowledge at the extreme ends of any physical distribution. To measure the diameter of IC 11.1 with confidence, an observer must first obtain a deep optical or near infrared image of the region around Abell 2029, an image with sufficiently long total exposure time that very faint extended emission is detected above the noise floor. This image must then have the sky background subtracted with extreme precision the contribution of atmospheric emission, scattered zodiacal light, and unresolved background galaxies must be estimated and removed, leaving only the emission associated with IC 11.1 and the surrounding cluster. This subtraction is performed using blank regions of sky within the same image, assumed to represent empty sky. But the outer halo of IC 11.1 is itself so extended that it may contaminate even distant regions of the image used for sky estimation. An observer who uses sky regions too close to the galaxy will underestimate the sky background and measure a larger apparent diameter. An observer who uses sky regions at radii, where IC 11.1's halo actually contributes measurable flux, will overestimate the sky background and measure a smaller apparent diameter. This systematic uncertainty is not easy to eliminate, and it contributes significantly to the spread in diameter estimates in the published literature. A related challenge involves the distinction between IC 11.1 itself and the intracluster light distributed throughout Abell 2029. This distinction requires knowledge of the three-dimensional distribution of stars in the cluster, which stars are gravitationally bound to the central galaxy, versus which are in the broader cluster potential. This three-dimensional distribution cannot be observed directly. It must be inferred from the projected two-dimensional surface brightness distribution combined with dynamical models. The degeneracy between model parameters at low surface brightness is substantial, and different modeling choices produce different conclusions about the fraction of observed surface brightness attributable to IC 11.1 versus the intracluster light. These are not objections to the claim that IC 11.1 is extraordinarily large. They are descriptions of the genuine uncertainty bands around the measurements. The best current evidence suggests a diameter between approximately 5 and 6 million light years, with the outer portions of that range more uncertain than the inner. The galaxy is genuinely extraordinary. The precision with which we can characterize it is limited by physics, the physics of photon statistics, sky backgrounds, and galaxy (ICL) decomposition, rather than by any failure of observational effort or skill. More fundamentally, The question depends on what is counted as part of the galaxy and what is counted as intracluster light. In a dense cluster environment, stars are constantly being stripped from infalling galaxies and distributed throughout the cluster volume in a diffuse component that is not gravitationally bound to any single galaxy's potential. This intracluster light, the ICL, can account for 10 to 30% of the total stellar mass in a rich cluster, distributed in complex asymmetric patterns that reflect the cluster's merger history. The outer stellar envelope of a CD galaxy like IC11-1 grades smoothly and continuously into the ICL. There is no clean physical boundary separating stars belonging to IC1101 from stars belonging to the intracluster medium. The measurement of IC11-1's diameter is therefore, at some level, a measurement that depends on a definitional choice about where to draw that boundary. Different observers using different analysis methods, different aperture choices, and different surface brightness thresholds have produced estimates of IC1101's diameter, ranging from roughly 4 million light-years to over 6 million. The spread in these estimates is not primarily a consequence of measurement error in the sense of instrumental noise. It is primarily a consequence of this definitional ambiguity, combined with the technical challenge of accurately subtracting the sky background when measuring extremely low surface brightness features. This is not a criticism of the science. It is an accurate description of the state of knowledge, and it illustrates a general principle at the extreme ends of any physical distribution. The measurements become correspondingly uncertain, and the object being measured grades imperceptibly into its environment. What can be said with confidence is that IC1101 is the most massive and spatially extended individual galactic system for which measurements of the relevant precision currently exist in the observable universe. Whether future surveys with better surface brightness sensitivity will find comparable or larger systems elsewhere in the observable universe is unknown. Future facilities such as the Vera C. Rubin Observatory, whose legacy survey of space and time will image the southern sky repeatedly over 10 years with a sensitivity to extended low surface brightness emission unprecedented for an all-sky survey, will likely either confirm IC1101's uniqueness or identify additional candidates of comparable or greater extent. The question will not remain permanently open. It will be answered progressively better as the relevant instruments come online. The possibility that larger galaxies exist beyond the currently measured population in regions of the observable universe not yet imaged with sufficient depth is more than merely a theoretical concern. The observable universe contains approximately 1 to 2 trillion galaxies, a number that represents not only the enormous total galaxy population, but also the enormous incompleteness of current surveys. Even the most complete surveys at moderate redshift cover only a small fraction of the observable volume with the depth required to characterize low surface brightness features. The fraction of all CD galaxies in rich clusters that have been observed with the precision needed to establish whether their stellar halos exceed IC1101's is very small. There may be comparable or larger objects sitting in rich clusters in the observable universe that have not yet been imaged with the necessary depth. The statement that IC1101 is the largest known galaxy is accurate. The statement that it is the largest galaxy in the observable universe is an inference about an incompletely surveyed volume. And beyond the observable universe, beyond the cosmological horizon set by the age of the universe and the finite speed of light, the question of largest galaxy becomes philosophically rather than merely scientifically open. If the universe is spatially infinite, as current observational evidence is broadly consistent with, then every possible extreme in the distribution of galaxy properties is realized somewhere. A galaxy with a diameter of 10 million light-years or 50 million or more. Such objects, if the physical processes that produce them are not truncated at IC1101 scale, may exist somewhere in the infinite volume of the cosmos beyond our horizon. We will never observe them. They cannot communicate with us. In any practical epistemic sense, they do not exist in the same sense that IC1101 exists. They are implications of a mathematical extrapolation applied to a universe whose extent we cannot observe, not objects within our scientific reach. This asymmetry between what exists and what can be known is one of the defining features of cosmology as a science, and it becomes acute when discussing extreme objects like IC 1101. The observable universe is a sphere of finite radius determined by physics, and that sphere is our world in the deepest sense. Everything within it is, in principle, accessible to investigation. Everything beyond it is, in principle, permanently inaccessible. The largest galaxy in our observable sphere is the largest galaxy in our cosmos, in the only cosmos we will ever have access to. The structures at still larger scales within the observable universe, above the level of galaxy clusters and individual galaxies, provide a useful and humbling perspective on IC 1101's place in the full hierarchy of cosmic structure. Galaxy clusters, as large as they are themselves organized into superclusters, aggregations of multiple clusters connected by filaments of the cosmic web. The Virgo supercluster, the supercluster that contains the Milky Way's local group, extends roughly 110 million light years in diameter and contains several dozen galaxy groups and clusters. This is a single supercluster, spanning a distance that would require IC 1101 placed end-to-end approximately 20 times to bridge. In 2014, using the peculiar velocity field of galaxies, the component of each galaxy's motion that deviates from simple Hubble expansion, Brent Tully and collaborators identified a structure of still greater scale, the basin of gravitational attraction within which our local group sits. They named it Laniakea, from the Hawaiian word's meaning, immeasurable heaven. Laniakea is the watershed of gravitational infall centered on the Great Attractor, a region of concentrated mass near the Norma cluster, toward which the peculiar velocities of galaxies throughout our local volume converge. The full extent of Laniakea, defined by the basin of this convergent flow, is approximately 500 million light years in diameter, containing the equivalent mass of roughly 100 million billion solar masses, approximately 100,000 large galaxies. Laniakea is not a gravitationally bound structure in the sense that IC 1101 or Abell 2029 are bound. The expansion of the universe will eventually overcome the gravitational flows that define it, and the supercluster will disperse over tens of billions of years. But as a dynamical structure, a region of space currently organized around a common gravitational basin, it is real and measurable. IC 1101 and Abell 2029 are not part of Laniakea. They lie approximately 1 billion light years away in a different region of the cosmic web, separated from our local supercluster by a distance comparable to Laniakea's own diameter. The two structures are, in a practical sense, in different cosmological neighborhoods, regions that have evolved largely independently, connected to each other only by the very large, scale structure of the cosmic web, rather than by any local gravitational relationship. On scales above Laniakea, the structure of the universe is described by filaments and walls of the cosmic web, the Sloan Great Wall, identified from early Sloan Digital Sky Survey data, spanning roughly 1.37 billion light years. Larger structures at the boundaries of observational confidence, whose coherence as physical objects rather than statistical patterns in sparse data remains debated, and ultimately the entire observable universe, whose matter distribution on the largest scales approaches homogeneity. The universe looks roughly the same from any vantage point, when averaged over volumes of several 100 million light years or more. This approach to homogeneity at large scales is one of the foundational observational facts of modern cosmology, and it stands in stark contrast to the dramatic inhomogeneity visible on smaller scales. The contrast between dense filaments and empty voids, between rich clusters and field galaxies, between the extraordinary concentration of IC 1101 and the diffuse emptiness of the voids surrounding it. IC 1101 exists precisely because the universe is inhomogeneous at cluster scales. It is the product of a region of enhanced primordial density that became Abell 2029, a region that started slightly denser than its surroundings, attracted more matter, grew denser still, and over 13 billion years became one of the most concentrated gravitational environments in the observable universe. The galaxy at its center is the product of the same process taken to its extreme, an object that has accumulated matter from across millions of light years, that has consumed hundreds of smaller galaxies, that has been building continuously since long before the Earth existed, When IC 1101 is described as the largest known galaxy in the observable universe, it is easy to hear that description as a statement about a record, an entry in a catalogue of superlatives, a champion identified and classified and filed away. But that framing misses what is most interesting about the object. IC 1101 is not merely the largest item in a list, it is the endpoint, the current endpoint, the endpoint accessible to our observations at this moment in history, of the gravitational process by which the universe organizes matter from diffuse primordial plasma into concentrated, complex, hierarchically structured systems. It is what the universe does, pushed to one of its current extremes. The Milky Way is also what the universe does, at a different location in the distribution of outcomes, but following the same physical laws, operating by the same processes, shaped by the same initial conditions. IC 1101 and the Milky Way are not different kinds of objects. They are different outcomes of the same process, separated by 11 billion years of merger history and a factor of 1,000 in stellar mass. The light from IC 1101 that enters any telescope pointed at Abell 2029 today departed from IC 1101 approximately 1,070 million years ago. The universe at that time was roughly 12.5 billion years old. The first complex multicellular animals were just beginning to diversify in Earth's Cambrian oceans. The photons carrying information about IC 1101's stellar distribution have been traveling through expanding space ever since, stretching as the universe expanded, their wavelengths lengthening in the cosmological redshift that Hubble first measured, and that remains one of the most direct observational demonstrations of the universe's expansion. By the time those photons arrive at a detector on Earth, their wavelengths have been stretched by a factor corresponding to the cosmic expansion over 1 billion years of travel. Astronomers must correct for this redshift when interpreting the observed colors of IC 1101's stellar population and when estimating its distance using Hubble's law. What IC 1101 looks like today, what state it is in as you read this, as you contemplate its scale, is unknown and will remain unknown for approximately 1 billion more years. The universe does not provide real-time information about its distant contents. Every observation is an observation of the past, and the more distant the object, the more ancient the information. We see IC 1101 as it was 1 billion years ago, and we must infer its current state from our understanding of how such objects evolve on billion-year timescales. By now, it has likely continued accreting, continued fading as its stellar population ages, continued expanding its outer halo through additional minor mergers. But whether any significant event, a major merger with another large cluster galaxy, an episode of renewed AGN activity, some unexpected perturbation from the surrounding cluster environment, has altered its structure in the intervening billion years, is simply not something we can currently know. There is a specific kind of intellectual discomfort that arises when these facts are absorbed together, not the discomfort of ignorance, but the discomfort of scale. The Milky Way, a galaxy containing hundreds of billions of stars, is itself so large that light takes 100,000 years to cross it, so ancient that its earliest stars formed before the solar system existed, so massive that it contains more free electrons than there are grains of sand on all the beaches of Earth. And yet IC 1101 makes the Milky Way look small, not metaphorically small, geometrically, physically, measurably small. And Abell 2029 makes IC 1101 look like a single component in a much larger structure, and Laniakea makes Abell 2029 look like a single cluster in a broad flow pattern. And the observable universe makes Laniakea look like a local feature in an almost incomprehensibly vast expanse. And all of this, every galaxy, every cluster, every supercluster, every filament of the cosmic web, every void and wall in the large, scale structure of the observable universe, exists within a sphere of 46 billion light-years radius. Beyond that sphere, in the universe that we cannot observe, the process continues. If the universe is infinite, and current observations are consistent with, though not proof of, an infinite universe, then every scale we can imagine is, somewhere in the whole of space, exceeded. The largest galaxy we have found is a local maximum in our observable sample, not the global maximum in an infinite distribution. The honest confrontation with IC 1101 is therefore not a confrontation with the biggest thing. It is a confrontation with the nature of scale itself, with the fact that the universe does not organize itself according to any scale that is meaningful to a species that evolved to navigate a world measured in meters and kilometers. Human intuition calibrates itself to the environment in which it evolved: the savanna, the village, the horizon visible from a hill. It extends with effort and education to the scale of a city, a continent, a planet. It fails, almost completely, when asked to viscerally absorb the difference between 100,000 light years and 6 million, between a billion solar masses and 100 trillion. These numbers are not merely large. They are large in a qualitatively different sense from the large things of ordinary experience. The distance to the nearest star is large. The age of the universe is large. The number of atoms in a gram of carbon is large. These things can be computed, compared, reasoned about, but they resist being felt in the way that the size of a mountain or the depth of an ocean can be felt by a body that has stood on the one and looked out across the other. The scale of IC 1101 is not the kind of large that yields to contemplation and eventually becomes intuitive. It is the kind of large that remains, permanently, beyond the reach of any human faculty for direct apprehension. What we can do, what science allows us to do, is reason about it accurately, even when we cannot feel it truly. In that gap between what can be reasoned and what can be felt, much of cosmology lies. The numbers are precise, the comprehension is imperfect, the universe continues regardless. Before moving outward from IC 1101 to the even larger structures that dwarf it, it is worth dwelling on one aspect of the galaxy's nature that tends to be underemphasized in discussions focused exclusively on its size: the relationship between what we can see and what is actually there, the ratio of luminous to dark matter, and what that ratio implies about the true nature of IC 1101 as a physical system. The stars of IC 1101, all 100 trillion solar masses of them, burning and cooling across millions of light years of space, are not the majority of what constitutes IC 1101. They are the visible component, the luminous tracer that announces the galaxy's presence across a billion light years of intergalactic space. But gravitational lensing studies, stellar velocity measurements, and X-ray observations of the surrounding cluster gas all converge on a picture in which the stellar mass of IC 1101 is a minor fraction of the total mass enclosed within the galaxy's extent. Dark matter, the gravitationally active but electromagnetically invisible component of matter that makes up approximately 85% of all matter in the universe, constitutes the dominant mass component of IC 1101, just as it does in every galaxy from the smallest dwarf spheroidals to the largest CD systems. The dark matter halo of IC 1101 is not directly observable in any electromagnetic wavelength. Its existence is inferred from the gravitational effects it produces, the velocities at which stars orbit in the outer regions of the galaxy, velocities that are too high to be explained by the gravitational pull of the visible stellar mass alone, the temperature and distribution of the hot intracluster gas, which traces the gravitational potential including its dark matter component, and gravitational lensing, in which the mass of IC 1101 and its surrounding cluster bends light from background objects, producing distortions that allow the mass distribution to be mapped independently of its luminous content. The dark matter halo of IC 1101, if it could be rendered visible by some hypothetical means, would extend far beyond the already extraordinary 5 to 6 million light-year radius of the detectable stellar halo. In the most massive systems, dark matter halos extend to radii comparable to or exceeding the virial radius of the cluster, the radius within which the mean density equals a specific multiple of the critical density of the universe, often used as the effective boundary of the cluster. For Abell 2029, this radius is roughly 10 million light-years. The dark matter halo of IC 1101 bleeds continuously into the broader halo of the cluster, and separating the two is partly a question of definition. What is certain is that the physical influence of IC 1101, its gravity, its dark matter halo, its heating of the intracluster medium, extends across a region that substantially exceeds even the remarkable 5 million light-year diameter of its stars. This distinction between visible and gravitational extent applies at every scale in the universe. Galaxies are smaller than their dark matter halos. Galaxy clusters are smaller than their virial radii. The cosmic web filaments are defined by dark matter density, with luminous matter tracing, but not exhausting the full dark matter distribution. If we could see the dark matter, if it emitted or interacted with light in proportion to its mass, the universe would look almost unrecognizably different. The densest regions would glow with a luminosity reflecting their true mass rather than just their stellar content. The cosmic web would appear far more pronounced, with filaments and nodes of tremendous brightness marking the dark matter skeleton, underlying all large-scale structure. IC 1101 would appear vastly larger and more massive, a gravitational behemoth whose true extent encompassed a significant fraction of its surrounding cluster. The stars we see in the night sky, in the Milky Way and in distant galaxies like IC 1101, are a thin luminous skin on an invisible dark matter universe. This is not merely a philosophical observation about our epistemic limitations. It is a statement about what the universe actually is. The ordinary matter from which stars, planets, gas, and people are made constitutes roughly 5% of the total energy content of the universe. Dark matter constitutes roughly 27%. Dark energy, the even more mysterious component responsible for the accelerating expansion of the universe, makes up the remaining 68%. The universe we can see in any electromagnetic wavelength represents a small fraction of what is actually there, and the universe we think we understand is smaller still. For IC 1101 specifically, the dark matter context is essential to understanding its formation history. The merger of dark matter halos drives the merger of the galaxies embedded within them. When two dark matter halos merge, the galaxies they contain are carried along, their mutual approach facilitated and accelerated by the dynamical friction operating within the combined dark matter structure. The sequence of galactic mergers that built IC 1101 was, at a deeper level, a sequence of dark matter halo mergers. The visible stellar events were consequences of a dark matter architecture that assembled itself over billions of years, drawing ordinary matter along as a luminous tracer of the underlying gravitational dynamics. The formation of IC 1101 is therefore the story of a dark matter halo that grew, through hierarchical merging, to extraordinary mass, one of the most massive individual dark matter halos in the observable universe, sitting at a rare and privileged position in the cosmic web. The stars that now fill IC 1101 did not arrive there spontaneously. They formed in smaller halos in the progenitor galaxies of the current merger tree, and were transported to their current positions by the gravitational dynamics of halo mergers carried out over most of cosmic history. The galaxy is, in this sense, an archive. Its stellar populations and their distribution in space encode information about the galaxy's entire assembly history, about the succession of mergers and accretion events that brought each stellar population from its place of formation to its current orbit within the vast ellipsoidal structure of IC 1101. Raiding that archive is one of the objectives of modern spectroscopic surveys of massive elliptical galaxies. The ages, chemical compositions, and spatial distributions of stellar populations within a galaxy carry information about when and where those stars formed. Old, metal-rich populations in the center suggest early formation in a gas-rich environment. Younger populations in the outer halo might indicate more recent mergers with lower mass systems. Spatial gradients in metallicity, the abundance of elements heavier than hydrogen and helium, provide constraints on whether the galaxy assembled primarily through in situ star formation or primarily through the accretion of externally formed stars. For Locke, the precision of such measurements is limited by its distance. Spectroscopy of individual stellar populations at 1 billion light years requires the combination of large aperture and long exposure times that strains even the most powerful current spectrographs. But the broad outlines of its stellar population structure are consistent with what is expected for a massive CD galaxy, old red, metal-rich, and assembled primarily at high redshift with subsequent growth through minor mergers. The radio properties of IC 1101 add another dimension to the portrait. Radio observations reveal that IC 1101 is a source of low-level radio emission, consistent with a currently low luminosity AGN in the nucleus. Likely in the radio, mode feedback phase in which relativistic jets carry energy into the surrounding medium without the dramatic optical luminosity of a quasar. The extended radio structure, if present, would be expected to correspond to the X-ray cavities observed in the intracluster medium, regions where AGN jets have inflated bubbles of relativistic plasma into the surrounding hot gas, displacing it and creating depressions in the X-ray emission. These radio mode AGN are the primary suspects in the feedback cycle that maintains the intracluster medium at temperatures above the cooling threshold and suppresses the cooling flows that simpler models predict. The energy budget of this feedback is substantial. The mechanical power required to inflate the cavities observed in the X-ray emission of clusters like Abell 2029, estimated from the PV work done against the surrounding pressure by the expanding radio lobes, is typically in the range of 10 to the 44th or 45th eggs per second, comparable to or exceeding the X-ray luminosity of the cool core. This is enough power, if efficiently coupled to the surrounding gas, to offset the radiative cooling losses that would otherwise lead to a cooling flow. The fact that this balance is maintained, that cool core clusters like Abell 2029 show cooling, but not the dramatic runaway cooling predicted by early models, suggests that the AGN feedback is doing exactly this, keeping the energy budget in approximate balance across scales ranging from the kiloparsec scale jets near the central black hole to the hundreds of kiloparsec scale of the cluster cool core. None of this mechanical power is visible in the ordinary sense. The radio lobes of IC11-1's AGN, if present at detectable levels, would be observable as extended emission at frequencies of a few hundred megahertz to a few gigahertz, low frequency radio waves that pass through the Earth's atmosphere but that carry no visible light. The X-ray cavities are visible only in X-ray imaging, at photon energies thousands of times higher than visible light. The hot intracluster gas that IC11-1's AGN is heating glows in X-rays and is invisible in any optical telescope. The dark matter halo that encompasses the entire system is invisible in every wavelength. A galaxy of extraordinary scale and mass, embedded in an even larger dark matter and hot gas structure, controlling the thermal evolution of a volume of space measuring millions of light years across, and in ordinary optical light, it appears as a moderately bright elliptical galaxy near the center of a cluster field, somewhat concentrated, somewhat fuzzy at its edges, unremarkable to an untrained eye. The multi-wavelength portrait of IC11-1 is, in this sense, a microcosm of the broader lesson of modern astrophysics. The universe is almost entirely invisible to unaided human senses. What we see in the optical window, the narrow slice of the electromagnetic spectrum to which human eyes are sensitive, the range of wavelengths between roughly 400 and 700 nanometers, is a small and often unrepresentative sample of what is physically present. The energy in the hot intracluster medium of Abell 2029 exceeds the energy in the optical emission of all the cluster's galaxies combined. The mass in the dark matter halo exceeds the stellar mass by an even larger factor. The universe that reveals itself to the naked eye on a dark night is a projection of the actual universe onto a very narrow window of perception, and beyond that window lies an enormously richer and more massive reality. For IC11-1, this means that the numbers cited in its public description, diameter of 5 to 6 million light years, stellar mass of 100 trillion solar masses, while genuinely extraordinary, describe only the tip of an iceberg. The full iceberg, including dark matter, hot gas, the extended intracluster light blending into the ICL, and the AGN feedback system driven by the central black hole, is a system of far greater total mass, far greater physical extent, and far greater energetic activity than the visible galaxy alone suggests. It is also a system that is not static. IC11-1 is continuing to evolve on timescales that are long by human standards but short by cosmological ones. The cluster Abell 2029 is still accreting material from the surrounding cosmic web. Galaxies are still falling in along the cluster's filamentary connections to the larger cosmic structure. Some fraction of these infalling galaxies will eventually be disrupted by tidal forces and contribute their stellar material to IC11-1's growing halo. The central black hole will occasionally be fed by cooling gas from the cluster core, producing brief episodes of AGN activity that heat the surrounding medium and temporarily suppress further cooling. The stellar population continues its slow aging, its overall luminosity declining by a few percent per billion years as intermediate mass stars exhaust their fuel and leave the main sequence. On a still longer timescale, hundreds of billions to trillions of years, the story of IC 1101 has a predictable ending. The stellar population will continue to evolve toward a collection of dim red dwarfs and stellar remnants, white dwarfs, neutron stars, and black holes. The last active star formation will end as the last reserves of cold gas are exhausted or heated beyond the cooling threshold permanently. The dark matter halo will remain, a gravitational ghost of the structure that once contained 100 trillion solar masses of burning stars. And in the very far future, as the accelerating expansion of the universe increasingly isolates gravitationally bound systems from one another, IC 1101 and Abell 2029 will form an island. All the galaxies currently within the cluster's gravitational binding, drawing together against the relentless stretching of space, while the rest of the observable universe recedes beyond the cosmological horizon. The cosmic web dissolves, and the universe becomes an increasingly empty, cold, dark expanse populated by isolated gravitational islands surrounded by expanding voids. The eventual fate of IC 1101 is, in that distant future, a cold, dark mass of stellar remnants and dark matter, the final form of what was once the largest galaxy in the observable universe. Its central black hole will remain, perhaps growing slowly through the tidal disruption of the stellar remnants that passed too close to it, accumulating mass over timescales so long they have no correspondence in human experience. The physics of the very far future of the universe remains, in some ways, more uncertain than the physics of its formation. The timescales involved make direct observation impossible, and the relevant processes are, in some cases, still poorly understood theoretically. But the broad strokes of the story, a universe cooling, dimming, expanding, and eventually becoming dark, are as well established as any long-range cosmological prediction. IC 1101 does not know it is large. The stars in its outer halo do not experience the galaxy's extent. They orbit their local region of the halo on paths determined by the local gravitational potential, unaware of the billion-year journey that dispersed them there. The black hole at IC 1101's center exerts its gravitational influence over a region measured in light, days to light, weeks near its event horizon. Indifferent to the millions of light years of stellar halo surrounding the galaxy it anchors, the galaxy is not an experience, it is a physical fact. Its size is not an achievement, it is an outcome. It does not mean anything beyond what it is, a particular arrangement of matter that resulted from the operation of the laws of physics on particular initial conditions over a particular span of time. What the size of IC 1101 means, if it means anything, is something we project onto it. The meaning is ours. The disorientation that comes from genuinely grappling with IC 1101's scale is not a response to something the galaxy is doing. It is a response to the gap between the universe as it is and the universe as our cognitive architecture, shaped by 400 million years of vertebrate evolution on a small planet, implicitly expects it to be. That gap is not a defect to be corrected. It is an invitation to keep reasoning, to resist comfortable anthropocentrism, to remain genuinely uncertain about what we know and what we have merely not yet found. The largest galaxy we have discovered, 1 billion light years away, 5 to 6 million light years across, 100 trillion solar masses in stars, 10,000 times more massive than the Milky Way, at the center of a cluster containing a quadrillion solar masses of gravitationally bound material, sitting in a universe containing a trillion such galaxies, in an observable volume of space constituting some unknown but surely small fraction of the total universe, in a cosmos whose full extent, if it has one, we do not know and may never know. IC 1101 is the largest galaxy we have found. The universe almost certainly is larger than what we have found, and that, the permanent distance between our knowledge and the full scale of what is, may be the most honest description of our position that cosmology currently offers.